Hi everyone, in this video I'm going to talk about Fleury's algorithm. And what Fleury's algorithm does is it allows us to find explicit Euler paths or circuits for a given graph, assuming Euler's theorem for paths or circuits is satisfied. Let's just go through it and figure out how it works. We'll do this on a couple of examples, and then I think you'll get the hang of it. So one is the preliminaries. We're going to follow a step-by-step process. First is we're going to check that Euler's theorem holds. So now what does that mean? That means that if you're looking for a Euler path, you need a connected graph and you need to have two vertices that are odd and every other vertex has to be even. That's if you're looking for a path that is not a circuit. And if you are looking for a circuit, you need every single vertex to be even in order to find an Euler circuit. And the graph, of course, needs to be connected. So the start is to then choose a starting vertex. So if you're going to find an Euler, any path, you need to start somewhere. And so choose a starting vertex. And here, when you make such a choice, you need to be thoughtful if you are in the path case. So if you're looking for a path, if you're looking for a path, which is not a circuit, um, your starting vertex must be odd. Choose an odd vertex. Okay, great. And then there's some intermediate steps. And what are the intermediate steps? Well, you'll be at some vertex and you look at, so when you reach vertex, you reach a vertex, find any edge connected to it, which is not a bridge. Not a bridge. Unless the only edge connected to it is a bridge. Only edges are bridges. Okay, then what do you do? So like now you've and then just pick one of those, and then pick one of those. If you're in the case where their only edges are bridges, pick one. Pick one. That's the next edge in your path. This is the next edge. Remove it and continue with the other vertex or with the next vertex. And then end when you can't go anywhere. And not move. You're done. All right, let's see how this works in examples. And I have one written here. So I'm going to move it down a bit. And I'm going to draw two versions of this. I'll put this one that has the full picture, and then I'll put another one where I'll remove edges as I go. All right, so the first thing to do is to check to see if um, Euler's theorem holds. That's my preliminaries that I need to do. And so for that, I need to write down my degrees. And let's recall what that looks like. I just need to find the number of edges that are connected to any given vertex. So this A has 3, B has 4, C has 2, D has 4, E has 3, and F has 4. So Euler's theorem for circuits says there are no circuits because I have an odd vertex. But since I have actually two odd vertices, that means that Euler's theorem for paths says that there can be, that there is an Euler path, that there exists an Euler path. Furthermore, it says that there exists an Euler path from A, one of the odd vertices, to say D, the other, oops, not D, pardon me, E, the other odd vertex. Okay, so I've determined that there, by Euler's theorem, because I believe in it, that there exists uh, an Euler path from A to E. So now what I want to do is I want to find that Euler path. And how am I going to do that? Well, here's what I'm going to do. I'm going to follow Fleury's algorithm. But the way I'm going to do it is on the left-hand side of the graph that we're looking at, I will number the edge in the path. On the right-hand side, I will actually remove that edge so that I can understand what I'm doing next. Because Fleury's algorithm is all about sort of removing edges as you go, so that you know they're gone. So I'm starting at A, and I don't have any bridges connected to A because I remove any one of those and it's still connected. So let's say I take A to D. That's my first edge. So now I'm going to remove on my right-hand side this AD. Great. Now I'm at D, and I look over here, and I look at any edge. I've got these three edges. None of them are bridges, so I can choose at random of one of them, and I will choose D to F. So I'll label that, oops, I will label that 2, and I will remove it as Fleury's algorithm tells me to. And now I'm at the vertex F, and if I look, I've got 3 edges coming out of F. Sorry, that's turned to blue. And again, none of these give me a bridge. Let me choose the one going to B. So I will choose this as my third, and I will remove it as I'm instructed to do. Now I'm back at B. I've traveled to B. And so now I have to look and see what is coming out of B. I've got 3 edges coming out of B. None of them disconnect. Let me go to A. Well, actually, let's go to B. I'll go to C, pardon me. So I'll go to C, and I'll say that this is my 4th edge, and I remove it. Now I'm at C. I don't have any choice. There is a bridge for the first time now. This edge here is a bridge. When I disconnect it, C is taken out. It's an isolated vertex. So all of a sudden, I am in a situation where I see a bridge, but I just take it. Since there are no other options, that's the one I'm taking. So I take it, and when I take it, I'm going to number it. I'm going to remove it. Oops. And I'll number that CD as my 5th edge. Now I'm at D. Again, I have only one option. I label that 6, and I remove it. Now I'm at E, and you might be able to see what's going to happen now. You're going to go around this sort of. You only sort of have one way. Well, you have 2 ways to go here, but yeah. Okay. So We're at E. Let's continue. We're at E. We can go this way or this way. Neither of these are bridges. We'll just choose to go to F. And so we go to F. That's our seventh. We remove it. Now we're in that situation again where we have a bridge, but it's the only option. That's 8. We remove it. We are at A now, and we only have one option. That's 9. We remove it. And then finally, we have only one left, and that's from B to E. And yes, so we go ahead and we remove that as well. And we'll label that 10. And you can see that all of the edges in our graph have been labeled uniquely, and that if we start at A, pardon me, we start at A and continue, we can go 1, 2, 3, 4. Oops, I messed it up. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and when we have that picture, we can see that we've indeed completed um, uh, a Euler path. We've hit every single edge exactly once. And if you follow this algorithm on the right-hand side, as you've removed, you'll have removed all of those edges. So you'll see that you indeed do get every single edge once. Wonderful. So I have another example here, which is kind of a pretty graph. And this example is really more about just checking the preliminaries, but we'll go ahead and go through it. All right, so let's take a look at this example. Well, I'm going to write down the degrees of these. And if you look, you can see that the degree of this is 4, the degree of an inner one is 4. In fact, if you look at every single vertex, you'll see that the degree of every single vertex is 4. And so I'm not going to go through that, but I'll just say, I'll just state it, degree of all vertices is 4. And that's actually, we have a name for graphs like that. They're called regular. And so this is an example of a regular degree 4 graph. All right. Nonetheless, what we're interested in is we're interested in finding an Euler path or an Euler circuit. And in this case, we have all even vertices. So every vertex has degree 4. That means every single one is even, which means we're in the case where we can find an Euler circuit. So, and recall, an Euler circuit is a path. It's an Euler path. It hits every single edge exactly once, and you end where you start. And so you might ask, where are you going to start? That is a question which is open to you, and you can choose anywhere you want. So I don't know, we'll choose down at the bottom here. Why not? And then you proceed exactly in the same way as you proceed with uh, with the path case. So we just choose, we erase, we choose. So I'm going to choose this. We erase. Oops. We choose 3 here. We erase. We choose, say 4 here. We erase. We're now over here, and we choose. We'll just choose to go back. Why not? 5 here. Oops. 5 here. We'll erase. The only thing you have to be a little careful about is making sure that you are not, that you're not choosing a bridge if there are other options available. So let's take a look. So I'll choose 6 here. I'll erase. Um, I'll choose 7 here. I'll erase. I'll choose let's see here. Eight here. Here. I'll erase. And I will choose 9 here. Great. And I will erase. And now I'm finally in this situation where we have to actually think for just a second. So everything up to this point, I've kind of randomly chosen an edge, but now I'm really in this part of Fleury's algorithm where we have to pay a little attention. So let's recall what this intermediate step is. So when I reach a vertex, find any edge connected to it, which is not a bridge, unless we have only a bridge to choose from. So now we're in that situation where actually we have options. Where right now what have we done? We've gone 1, 2, 3, 4, 5, 6, 7, 8, 9. We're right at this vertex. So we're right here, and we have 3 edges connected to it, 2 of which are not bridges, and 1 which is a bridge. This is a bridge. If we delete that, then we have this graph. So let's take a look, just in case people can't quite see it. I'm just going to do a little picture over here on the side. If I delete this graph, right, and what can I do? Well, I can look and you can pull this apart. You can see that deleting that graph gives us 2 disconnected pieces. And so that means that or deleting that edge, that means that this particular edge right here is a bridge. A bridge is any edge which you remove before it was connected, now it's disconnected. So we have one edge, and then we have 2 one bridge and 2 non-bridges. And we're at that vertex. Fleury's algorithm says that in this case, we have to choose something that is not the bridge. So if we can choose it, we choose it to be not a bridge. Okay, so now I will choose 10 here, the non-bridge. I'll delete it. Now I'm sort of forced. Now I actually have a bridge going from here to here, because once I delete that, this is by itself, but it's the only thing I can choose, so I just choose it. If you have a bridge as your only option, you choose that as your only option. It's only when you don't have it as your only option that you choose something else. So we delete that. We keep on going. 12. This is the only thing I can choose next. 13 is the only thing I can choose next. 14, the only thing I can choose next. And now somehow we've traveled back to that bridge. And again, we've kind of deleted a bunch of bridges along the way, but now we're back in that place where we're deleting that bridge, but it's our only choice. So we choose it. It's 15. And we delete that. Great. We are now down here. And again, we have this situation where again we have 2 possibilities. If we move along here, that is a bridge. It disconnects the connected piece. So we've got this. Whenever you have an isolated vertex, you just kind of discard it or forget about it. So here we don't want to choose this bridge because it's a bridge, and we have other options. These are not bridges, so we choose the one that's not a bridge. And so we are now at 15. We'll choose 16 here. I'll delete it. Now I'm sort of in a choiceless scenario. I'm deleting 18 here. I'll delete 19 here. I'll delete. And then finally 20 here, and I delete. And again, we've gotten back to where we started, and we've ordered all of our edges, and we can just go ahead and run through to make sure it works. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, 13, 14, 15, 16, 17, 18, 19, and 20. And we indeed have used every single edge exactly once and completed a full circuit. All right, so that's how to apply Fleury's algorithm. The reasons Fleury's algorithm really works aren't too bad. It's not too hard, but it does take a little bit of counting. And this is something we may do another time, but I think I'm going to leave this lecture for today.